Hello students, welcome to the EPG Pathshala. I am Ashok Goyal from the Department of Physics and Astrophysics, University of Delhi. Today we are going to discuss, in continuation of what we have discussed earlier, about the module Group Theory in Quantum Mechanics Part 2 from the paper Mathematical Physics. So, let us see what we are going to learn in this module. In this module, students, you will learn about the group theoretic connection between the reduction in symmetry of a quantum mechanical system due to perturbation. So when you apply a perturbation to a quantum mechanical system, it's expected that the symmetry is reduced. And with this reduction in symmetry, it's imperative that some degeneracy which existed before this perturbation will also be lifted. So based on purely group theoretic considerations, you would learn the selection rules governing the transition between different atomic levels due to the presence of this perturbation. So, let me discuss the topic of the perturbations and level splitting. Let's consider a Hamiltonian of a quantum mechanical system to be made of two parts, the total Hamiltonian being equal to h equal to h naught plus v, where h naught is the unperturbed Hamiltonian of the system, which is invariant under the symmetry group G. The total Hamiltonian h naught plus v will have a symmetry which is a subgroup of G, except in the case where the perturbation itself has the symmetry greater than or equal to the symmetry group G of H naught. What happens is that the total Hamiltonian in general has a symmetry less than the symmetry of the unperturbed Hamiltonian. The unperturbed Hamiltonian H naught in this case has a symmetry G, which is the symmetry of the total, and the total Hamiltonian has a symmetry H, and the energy levels of the system in this case will remain unchanged because the symmetry of the total Hamiltonian is the same or greater than the symmetry of the unperturbed Hamiltonian. In general, the symmetry group V will be smaller than the symmetry group G, and let the symmetry group of V be G prime, which let's consider it to be a subgroup of G. The total Hamiltonian H will now be invariant only under the symmetry transformation common to both the symmetry of the unperturbed Hamiltonian H naught and V, which means that G prime is also a symmetry group of H, of the total Hamiltonian H. Consider the perturbation V. If this perturbation has lower symmetry than the unperturbed Hamiltonian H naught, the total Hamiltonian will have a symmetry group G prime, which is a subgroup of G. G is the group under which the unperturbed Hamiltonian H naught is invariant, and V has a symmetry lower than H naught. Therefore, the total Hamiltonian, which is H naught plus V, will have a symmetry group G prime, which is a subgroup of G. Given a representation D alpha of the group G, the representation of the subgroup G prime can be obtained by selecting those representation matrices from among the representations D alpha G which correspond to the symmetry operations elements of G prime. So G prime has certain symmetry operations, G has certain symmetry operation. So we choose those representation matrices from the representation of the group G which correspond to the symmetry operations of the group G prime. Even if the matrices D alpha G form an irreducible representation of G, the representation of G prime called d beta G prime chosen may be reducible. This means that there is a subspace of basis vectors of d alpha G which is invariant under all transformations of the subgroup G prime. This means that even though the eigenfunctions belonging to the energy epsilon forms a basis of the irreducible representation of G. This representation will be reducible for the subgroup G prime and can be expressed in terms of the direct sum of the irreducible representation of the group G. The perturbation V will thus lift the original degeneracy and split the levels. Why? Because even though the eigenfunctions belonging to a particular energy E, it may form a basis of the irreducible representation of G. This representation reducible for the subgroup G prime. But G prime is a smaller subgroup and can be expressed in terms of the direct sum of the irreducible representation of the group G. The perturbation V thus will lift the degeneracy and split the level. We will illustrate this with the help of certain examples, but before that, a few mathematical preliminaries. Let alpha Lm and beta Km be the basis functions transforming according to the irreducible representations gamma alpha and gamma beta respectively of the group G. Let P hat Gi be a unitary symmetry transformation corresponding to the symmetry operation element Gi belonging to the group G. Then the scalar product of these basis functions alpha Lm and beta Kn is equal to alpha Lm P hat dagger G I into P dagger beta Kn. Thus the left hand side is independent of the group element. Since the left hand side is independent of the group element Gi, and how many group elements are there? N. Therefore, alpha Lm beta Kn, this scalar product can be written as 1 upon n sum over all elements I is equal to 1 to n of the matrix element P dagger, P hat dagger, P hat between alpha Lm and beta Km, which can be written in the form shown in the slide, and which by using the orthonormal properties we can write finally as alpha as sigma over Q and L I is equal to 1 to n alpha Pm beta Qn 1 upon n L alpha delta beta delta Q etc. Because of the orthonormality relation between the irreducible representations, we therefore finally have the scalar product alpha of these basis functions alpha Lm beta Km as delta alpha beta delta Lk and a reduced matrix element alpha P beta P. Thus the set of all eigenfunctions of the Hamiltonian which form the basis function of irreducible representations of a symmetric group form an orthogonal set. We now discuss the matrix element theorem and the selection rules. Let alpha Lm denote the eigenfunctions of the Hamiltonian H naught, that is the unperturbed Hamiltonian. When the perturbation V is switched off, so alpha Lm are the eigenfunctions of the unperturbed Hamiltonian. The effect of perturbation V is to lower the symmetry of the system, resulting into the splitting of the energy levels, as well as to induce transition of the system from one eigenstate to another. Let alpha Pm and beta Qn are eigenfunctions of H naught belonging to the irreducible representations of the group. When the perturbation V is applied, we can use the eigenfunctions of H naught, that is unperturbed Hamiltonian, to generate representations of the perturbation V. This is done by expanding the function V acting on the eigenfunction alpha Pm in a complete set of the eigenfunctions of the unperturbed Hamiltonian H naught. Thus, the effect of V acting on alpha Pm can be expanded in terms of a complete set of eigenfunctions of H naught as C alpha Pm beta Qn, we see the coefficient of beta Qn. The scalar coefficients C alpha Pm beta Qn can be determined by using the orthogonality relation of the eigenfunctions, namely the coefficient C alpha Pm beta Qn is given by the matrix element of V between these states alpha Pm and beta Qn, and the transition from the state alpha Pm to beta Qn will be forbidden if the matrix element of V vanishes. So if the matrix element of V between these two states vanishes, then there is no transition from the state alpha Pm to state beta Qn. This is the matrix element theorem. So if the perturbation V acting on the eigenfunction, which is represented by three quantum numbers alpha, P and M, so V acting on this state, if it does not contain the irreducible representation gamma B, the matrix element of V must vanish. And the transition then between this state alpha Pm and beta Qn under the perturbation V is forbidden. So what we are doing, we are saying we consider two states, alpha Pm and beta Qn. If V acting on alpha Pm does not contain the irreducible representation whose eigen functions are beta Qn, then this transition is forbidden. So the function V alpha Pm being a product of two functions V and the function alpha Pm, it generates a representation which is the direct sum of the representation of V and which is gamma V and of gamma. That is, gamma is the direct product of the representation of gamma V and gamma alpha, which can now be resolved in terms of the representation of gamma mu as a linear combination of A mu gamma mu, where gamma is expressed as the direct sum of the irreducible representations of the group G. Clearly, the matrix element of V will vanish if the direct product gamma V of gamma V into gamma alpha does not contain gamma beta. So thus, what we have learned is that the symmetry of the system forbids certain transitions under perturbation. And this also results in lifting of the degeneracy of the energy levels under the influence of this perturbation, which in fact reduces the symmetry. Now I will illustrate this with the help of an example. Consider a system having the symmetry of the group O, that is cubic group O. So a system has the symmetry which is the symmetry of the cubic group O. Now suppose we have a perturbation which reduces the symmetry to A, to a D3 symmetry, and B to a T symmetry. Remember, O has 24 elements. It's a group which is much bigger than the group D3 and T. So we have a system which has the symmetry O. Now the perturbation is applied. The perturbation reduces the symmetry from the cubic symmetry to a D3 symmetry or a T symmetry. In each case, we'll try to find out how the levels belonging to a 2 and 3 dimensional irreducible representation of O is split. Remember first, when the system has the symmetry group O, then its 2-dimensional representation means that it has 2 degenerate levels and another 3 doubly degenerate and triplet degenerate levels. So when this symmetry is reduced with the help of perturbation, then let us see how the energy levels split. First, look at the character table of the group D3. The D3 has 6 elements. It has 3 classes and 3 irreducible representations, 2 of dimension 1 and another of dimension 2. So these are the three character table is shown in the slide. Now, character table of the element D3. Now look at the character table of the group O. Then look in the group O, how does the character table of these elements of D3 look like? For example, the character table of D3 has 24 elements, but D3 has 6 elements. So we look at the elements E, C3 and 3C21 in the character table of O. And let us see how does this character table appear. So we have two one-dimensional irreducible representations with the correct A1, A2 with the characters 1, 1, 1 and 1, 1 minus 1 respectively. One two-dimensional reducible representation with characters 2 minus 1 and two three-dimensionals T1 and T2. Now from the table it is clear that this two-dimensional representation E is equal to E, which is that is irreducible representation of D3 containing the irreducible representation of O. So E contains E. The irreducible representation of D3 contains the representation A2 plus E. So T1 is equal to A2 plus E and T3 is equal to A1 plus E. So what does it mean? It means the irreducible representation of D3 contained in the irreducible representation of O can be determined from the character tables. And what do we find? We find that E is equal to E, T1 is equal to A2 plus E, and T2 is equal to A1 plus V. What does it imply? It implies that the two-fold degenerate level E remains unsplit when the threefold, while the threefold degenerate level belonging to the irreducible representation T1 of O splits into one D-dimensional and one twofold two-dimensional degenerate levels, transforming according to A1 and E. That means when the symmetry is reduced from the symmetry O to the symmetry D3, the energy level belonging to the representation T1, which triply degenerate, they split into one single degenerate level and one doubly degenerate level. Thus, the threefold degenerate levels belonging to the irreducible representation of O on the splits into one non-degenerate and one twofold degenerate energy levels, transforming according to the irreducible representation, say A1 and E of the group D. Now, look at the character table of we consider the other case where the group O, the symmetry of the group O is reduced by the perturbation to the symmetry of the group T. The group T has 12 elements in 4 classes, and its character table is before you in the slide. It has its irreducible representations are 4, the 3 representation of dimension 1 and 1 representation of dimension 3. The 2 representations of dimension 1 are mutually complex conjugate of each other. So the character table of T, whose irreducible representation were represented as A, E1, E1 star and T are given in the table, and you can see. Whereas the character of the element of T in the irreducible representation of O, what are the irreducible representations of the group O? They are A1, A2, E, T1 and T2. 2 representations, irreducible representation of dimension 1, 1 of dimension 2 and 2 of dimension 3. Its characters are given here. From here one can easily see that E is equal to E1 and T. We find that in this case the twofold degenerate level remains unsplit since it contains 2 complex conjugate pairs of one-dimensional E1 and E1 star levels. The threefold degenerate level belonging to the irreducible representation T1 and T3 of the group also remains unsplit. So in this case, the degeneracy of the levels belonging to the group O, both for two-dimensional as well as three-dimensional, remains unlifted. It's very interesting that even though the symmetry has been reduced from the cubic symmetry O to the symmetry group T, the degeneracy of the energy levels remain unlifted when the perturbation reduces the symmetry from the point group O to T. So I'll explain now the splitting of energy levels of atomic system in a situation where the symmetry is reduced, namely when the atom of the molecule is present in a crystal. So when an atom is placed in a crystal or when an atom is present in the molecule, the symmetry of the atom is reduced. Because remember, the isolated atom has the symmetry of the full rotation group, which is O3, whereas a molecule or a crystal has the symmetry of a point group appropriate to the molecule or the crystal. And remember that all the point groups are subgroups of the full rotational group O. The electronic levels in an isolated atoms have 2l plus 1 fold degeneracy corresponding to the irreducible representation dl theta phi of the group SO3. Now, these electronic levels would split when placed in a molecule or a crystal into levels which will correspond to the irreducible representations of the symmetry of the point group. And this is achieved by resolving the 2 plus 1 fold degenerate levels of the SO3 into the irreducible representation of the point group. Yet another example. Let us assume that the atom is placed in a cubic crystal with the octahedral point group symmetry O as before. We consider L is equal to 0, 1, 2, 3 levels transforming according to the dl phi theta irreducible representation. Remember that when you consider the energy levels transforming according to irreducible representation d alpha theta phi, the character of the group elements corresponding to the rotation about the z-axis, example for alpha, is given by chi, which is a function of the dimension L. So chi L of alpha is sine L plus half alpha divided by sine alpha by 2. This we have already seen. The character table of the group O, we have seen so many times. It has 5 classes and with 5 irreducible representations, 2 of dimension 1, 1 of dimension 2 and 2 of dimension 3. Its character tables are shown here. The character table of the classes of O in the 2l plus 1 dimensional irreducible representation d prime alpha of SO3. So what are we doing? So what we have in the situation is that we have a rotationally invariant system whose representations are the 2l plus 1 dimensional irreducible representation of dl alpha of the group SO3, because rotational invariant group SO3 in 3 dimensions. And then suddenly this symmetry is reduced to the cubic symmetry O. So we look at the character table of the classes of O in the 2l plus 1 dimensional irreducible representations of SO3. So SO3 has the representation corresponding to L is equal to 0, 1, 2 and 3. So these representations will give them the name D0, D1, D2 and D3. And character table of these classes of O, which are E, 8C3, 3C4, 2, 6C3, 6, etc. So the character table of the classes of O in this are given by 1, 1, 1, 1 and as shown in the slide as this. And you can see that, for example, the representation D0 is equal to the representation E in O. So E is the irreducible representation of O. The irreducible representation of SO3, D0 is equal to E, D1 is equal to T2, D2 is equal to E plus T1, D3 is equal to A2 plus D1 plus D2. So in the last column, we have resolved the irreducible representation of the group SO3 into the irreducible representation of the group O. So what do we learn from here? We see from this that a 5-fold degenerate D2 corresponds to L is equal to 2 irreducible representation, which is of dimension 5. This dimension 5 level, this D2 level, is splits into two levels in the cubic symmetry. One is a 2-fold degenerate level corresponding to the representation E, and another a 3-fold degenerate level corresponding to the representation T1 of the group O. And the 7-fold degenerate level D3 splits in the cubic 3-fold degenerate levels. We consider another example to obtain the splitting pattern of L is equal to 0 or L is equal to 1 atomic levels in the tetragonal group D4. That is, we have the atomic levels in a rotational symmetric environment labeled by L is equal to 0 and 1, and suddenly the symmetry is reduced to the tetragonal group D4. The character table of D4 is shown in the slide. It has 5 classes, 5 irreducible representations A1, A2, B1, B2 and E. The 4 are of dimension 1 and the 5th is a dimension 2. Now, the characters of the classes of D4, of which there are 5, in DL, because the original symmetry, for the original symmetry, the representations were DL, L corresponding to 0 and 1. So for D0 and D1 and also for D2 I have shown here, the character tables are given by this, which from here it is clear that D0 is equal to E, D1 is equal to A2 plus E, and D2 is equal to A1 plus B1 plus B2. What does it mean? It means that the 3-fold degenerate level D1 splits into one non-degenerate and one 2-fold degenerate level. And the 5-fold degenerate level D2 splits into 4 levels, namely 3 non-degenerate and 1 2-fold degenerate level. So let us summarize what we have learned. We have learned that purely based on the group theoretic considerations, we have shown that if the perturbation V has a lower symmetry than that of the unperturbed Hamiltonian, then this perturbation V will lift the original degeneracy and will split the energy levels. For example, the transition from the states alpha Pm to the state beta Qn will be forbidden if the matrix element of V between these states vanishes. This is the matrix element theorem. Thank you.